All right, let's talk about 4.8 partial fraction decomposition. This section may seem a little bit like, it may just seem a little bit strange, kind of like an oddball topic, but this is something that's going to be very important for you in calculus, especially second semester calculus when you start doing integration. Being able to perform some partial fraction decompositions are going to be very helpful for you. And it just may feel a little bit strange in this section, but now's the time to talk about them. Since we're talking about rational functions, now is the time to talk about partial fraction decomposition for sure. And there are some related topics in this section to what we've covered in the chapter. Like fundamental theorem of algebra, for example, is kind of sort of going to come up in a way that you may not have expected. But here's the idea behind partial fraction decomposition. Basically, we want to undo fraction addition or subtraction. And that's a little bit more difficult than it may seem, because when we do addition and subtraction of rational expressions, we have to have common denominators. And so we oftentimes do this crazy manipulation, and we end up with a very different looking expression than what we started off with, right? So what we want to do is we want to be able to go from here and somehow get back to there, if possible. Okay, so the way that we do that is we're going to say, all right, we want to find a and b so that this expression equals a over that factor plus b over that factor. Okay, and to find a and b, we can solve this by doing something like this, right? So we can multiply through by x plus 3 times x minus 1, and then that would just leave 5x plus 7 on the left-hand side. On the right-hand side, we get a times x minus 1, because the x plus 3's would cancel, and b times x plus 3, because the x minus 1's would cancel. And then we can distribute those, collect like terms, and we would get something like this: a plus b times x plus negative a plus 3b. And then we can equate the coefficients, right? So we can take this coefficient. We know that a plus b should equal 5. And we know that negative a plus 3b should equal 7. So we get these two equations that form a system. And we can solve the system. And if we solve the system, we discover that a equals 2 and b equals 3, just like we would have expected, right? Right? A equals 2 and b equals 3. So that strategy is called equating coefficients. That's called the equating coefficients method. Another method for solving this equation for a and b would be to plug in values for x that will cancel off the a term, and then plug in a different value for x that will cancel off the b term. I don't know what this is called. I don't know if there's an official name for it, so I'm just going to call it the cancellation method. But using the cancellation method on the same problem, right? So we're starting off with this. We want to decompose it, right? Multiply both sides by the denominator. We end up here. And now the cancellation method would work like this. We would think, well, what could I plug in for x that would cancel off the a term? And the answer is 1, right? If I plug in 1, this is going to be 0, and a times 0 is just going to cancel off. So if I let x be 1, then I get 5 plus 7 equals a times 0 plus b times 4. So in other words, 12 equals 4b, and that would mean b equals 3. Then I could do the same thing with b. I could say, well, what would I plug in here in order to cancel off the b, right? I would have to plug in x equals negative 3, right? Plugging in negative 3, I get 5 times negative 3 is negative 15 plus 7 equals a times negative 4 plus b times 0. So in other words, negative 8 equals negative 4a, so a equals 2. That's called the cancellation method. You're welcome to use either method. I think the easiest thing to do is to use some kind of combination of these two methods. Probably the cancellation method is easier when you're able to cancel everything off, but you're not always able to do that, and so you're going to end up having to solve some systems occasionally when you're doing partial fraction decomposition. So one issue that we need to address is what the decomposition is supposed to look like. We knew beforehand when we were looking at 5x plus 7 over x plus 3 times x minus 1, we knew beforehand that this looked like something over x plus 3 plus something over x minus 1. And so we set up this equation, right, to solve for a and b. But the format of the decomposition is not always that simple. So how do we know what format the decomposition should be? Well, before we answer that question, here are some terms that we need to define. In the previous example, the 2 over x plus 3 and the 3 over x minus 1 are called partial fractions. And 2 over x plus 3 plus 3 over x minus 1 is called the partial fraction decomposition of the original expression. Okay. Some other terms that might come in handy. A rational expression, p of x over q of x, is called proper if the degree of p is less than the degree of q. So it's kind of like a proper fraction, right? You have a proper fraction if the numerator is less than the denominator. So you have a proper rational expression if the degree of the numerator is less than the degree of the denominator. You have an improper rational expression whenever the degree of the numerator is greater than that of the denominator. When you have improper rational expressions, before you do the partial fraction decomposition, you need to do long division first, right? So you need to rewrite p over q as a plus r over q, right? Where r over q is a proper fraction. So you do that by performing long division. Okay? Now, to answer the question, how do we know what format the decomposition should be? Well, the fundamental theorem of algebra says that every polynomial has complex zeros. The conjugate pairs theorem says that the zeros of a polynomial with real coefficients come in conjugate pairs. So, taken together, the fundamental theorem of algebra and the conjugate pairs theorem imply that when a polynomial with real coefficients is completely factored over the real numbers, its factors are either all linear or quadratic. And that's important because it tells us that there are 4 types of factors to consider when performing partial fraction decomposition. So here are the 4 cases, and what I'm going to do is walk you through an example of each case, all right? But here are the 4 cases. So let's say that q of x is a polynomial with real coefficients, and that lowercase q of x is a factor of capital Q, when capital Q is completely factored over r. Then we can conclude the following. Little q is linear and is not repeated in the factorization of capital Q. Little q is linear and is repeated in the factorization of capital Q. Little q is quadratic and not repeated. Little q is quadratic and is repeated. Okay, so those are the 4 cases to consider. Q is linear and not repeated. Q is linear and is repeated. Q is quadratic and not repeated. Q is quadratic and is repeated. Those are the 4 possible cases. Okay. So I'm going to walk you through an example of each case. Okay, when we have linear factors that are not repeated, that's case 1. So the way that we handle the decomposition of each factor depends on the case it falls under. So we'll start with the simplest case, case 1, and we'll work our way up to the most complicated case, which is case 4. So if little q, case 1, if little q is linear and is not repeated, then the portion of the partial fraction decomposition of p over q that corresponds to little q is a over q of x. That's maybe sounding kind of confusing. Let me give you an example. So example 1 says, find the partial fraction decomposition of 3x plus 26 over x squared plus x minus 12. So the first thing that we're going to want to do is perform long division if the degree of the numerator is greater than the degree of the denominator. It's not in this case, so we don't have to perform long division. The next thing that we want to do is factor. Specifically the denominator, right? So the denominator here is going to factor as x plus 4 times x minus 3. The numerator doesn't factor, and it doesn't matter anyway. We usually don't really care about factoring the numerator when we're trying to perform partial fraction decomposition. So notice that in the denominator now, we've got 2 linear terms and neither of them is repeated. So these are both case 1 scenarios. that tells us that the partial fraction corresponding to x plus 4 is just going to be a over x plus 4. And the partial fraction corresponding to x minus 3 is going to be b over x minus 3. Right? So it's just some real number. I'm calling them a and b, but it's just some real number over x plus 4 and then some other real number over x minus 3. Okay? So we're going to say 3x plus 26 over x plus 4 times x minus 3 should be equal to a over x plus 4 plus b over x minus 3 for some real numbers a and b. To solve for a and b now, we would multiply both sides by x plus 4 times x minus 3, and we would get 3x plus 26 equals a times x minus 3 plus b times x plus 4. Now I'm going to use the cancellation method in order to solve for a and b. So if I wanted to cancel a, I would plug in 3 for x, right? So let x equal 3, and you get 9 plus 26 equals a times 0 plus b times 7. So in other words, 9 plus 26 is 35 equals 7b, and that tells us that b is 5. Okay, now if I want to cancel off b, I would plug in negative 4 for x. So let x equal negative 4. 3 times negative 4 is negative 12. Negative 12 plus 26 would be 14. Oh, maybe I'll just write it like this. Negative 12 plus 26 equals a times negative 7 plus b times 0. And that implies that 14 equals negative 7a, which implies that a is negative 2. Okay, so the partial fraction decomposition of 3x plus 26 over x plus 4 times x minus 3 is negative 2 over x plus 4 plus 5 over x minus 3. Okay, and that's that. You can write this in a different order, right? You could, of course, write this as 5 over x minus 3 minus 2 over x plus 4. That would be the same thing. You can't swap the numerators though, right? You couldn't put 5 over x plus 4 minus 2 over x minus 3. That would be wrong. Okay, but these are the partial fraction decompositions, and you can verify this, right? If you get common denominators here and then combine like terms and stuff, this is where you're going to end up. Okay, you're welcome to verify that in the home. But that's case 1. I say in the home. You are in the home, right? You're watching this lecture at home. Anyway, case 2 is when you have a linear factor that's repeated. Let's say that it's repeated m times. Okay. In that case, the portion of the partial fraction decomposition that corresponds to q, to little q, is going to be a1 over x minus a plus a2 over x minus a squared, and so forth. You would do this for as many times as the factor is repeated. Okay, so to give you an example, let's say that we wanted to find the partial fraction decomposition of this rational expression. Okay. All of 3 of these are linear factors. This one is only repeated once, this one is repeated 3 times, and this one is repeated twice. So the format of our partial fraction decomposition would look like this. We would have one copy of x minus 4, right? So a over x minus 4. Then we'd have 3 copies of x plus 1, but we increase the exponent each time. So we'd have 1 copy, b over x plus 1, a second copy, c over x plus 1 squared, and then a third copy, d over x plus 1 cubed, right? And then for this factor, we would have 2 copies, right? We would have an e over x minus 5, and then an f over x minus 5 squared, okay? So that's how that works. Now, to find a, b, c, d, e, and f, well, we're going to have to multiply through by the denominator, and then solve by equating coefficients, or by cancellation, or by some combination of those two two strategies. Okay. So let me give you a completely different example, though, rather than finishing that one. Let me give you a different example. So to start off with, we need to factor. Okay, we can factor out an x, and then I'm left with x squared minus 2x plus 1. So I have x plus 5 over x times x minus 1 squared, right? It's the x squared minus 2x plus 1 is just x minus 1 times x minus 1. Okay? Well, so let's set up the format of the partial fraction decomposition. We would say x plus 5 over x times x minus 1 squared would equal, well, for x, I'm just going to have one copy, right? An a over x. For x minus 1, I'm going to have two copies, right? One of them is going to be b over x minus 1, and the other one is going to be c over x minus 1 squared. Okay, now to solve this for a, b, and c, we multiply through by the denominator and get x plus 5 equals a times x minus 1 squared plus b times x minus 1, right? If you're imagining multiplying this times that, or I guess multiplying this whole expression times that, the x minus 1s will cancel, leave an x times x minus 1. And then you'd have c times the x plus x minus 1 squareds will cancel and just leave you with an x, right? You're left with cx. Okay? So now for the cancellation method, if I wanted to get rid of a, I might plug in 1 for x. And then I get 6 equals, that's gone, and c, right? So c equals 6 if I let x equal 1. If I let x equal 0, then I get 5 equals 0 minus 1 is negative 1, negative 1 squared is positive 1, 1 times a is a. That's gone, and that's gone. So a equals 5. How do I get b, though, right? Like, I'm not going to figure out what b is by canceling something off. I suppose that I could let x be some other number, right? I could say, let x be 2 or something like that. 2 minus 1 is 1, 1 squared is 1, so I get, I get 7 equals a plus 2 minus 1 is 1, 2 times 1 is 2, so 2b plus 2c, right? But I already know that a is 5 and c is 6. So really this means 7 equals 5 plus 2b plus 2 times 6. And then I can solve for b, right? So I can say 7 equals 2 times 6 is 12. 12 plus 5 is 17. And 7 minus 17 would be negative 10. Okay, so b equals negative 5. So there you go. I've got a, b, and c now. So my partial fraction decomposition, x plus 5 over x times x minus 1 squared, is a over x plus b over x minus 1 plus c over x minus 1 squared. Okay, and once again, you're welcome to work out the addition and subtraction here. You should end up here. Okay, you should end up there. Assuming that I did all my arithmetic correct. I'm pretty confident A and C are correct. B, yeah, I mean, it looks good. It looks good. So I think that's correct. Okay, so that's how case 2 works. Let's look at case 3. Case 3 is when you have a quadratic factor that's irreducible over the reals, and it's not repeated. Okay? So, when you have that situation, the portion of the partial fraction decomposition that is connected to Q, or that corresponds to Q, is going to be AX plus B over Q. All right? So whenever you have a quadratic factor, the numerator needs to be linear. That's the moral of that story. So let me give you an example of this. Let's say that we wanted to find the partial fraction decomposition of this thing, right? Well, x minus 2 is just a linear term, and it's not repeated, so we only have one corresponding factor to that, right? We say a over x minus 2. That's easy. X squared plus 1, on the other hand. Now, this is a quadratic factor, and it is not factorable over the reals. Over the complex numbers, you could factor it as x plus I times x minus I. But over the reals, this is as factored as it's going to get. And since it's a quadratic, that means that the numerator of the partial fraction for x squared plus 1, the numerator needs to be linear. So it needs to be bx plus c over x squared plus 1. Okay? And then x squared minus 1. Now this is not even fully factored over the reals. X squared minus 1 we can factor as x plus 1 times x minus 1. So that's a quadratic, yes, but it's not an irreducible quadratic. It can be factored. And if it can be factored, you should factor it. Okay? Now factoring it completely reveals that you've got a couple of linear terms. So this one is just going to have a d over x plus 1, and this one's going to have an e over x minus 1 attached to it, right? Or corresponding to it. Okay, and so this would be the format of the partial fraction decomposition of this thing up here. Okay? So let me give you another completely different example. This time we have to do a little bit of factoring first. So again, don't worry about trying to factor the numerator. For partial fraction decompositions, it doesn't matter. But you do need to factor the denominator. So I know I can take out an x, and if I do, I'm left with x squared plus 2. Now, the zeros corresponding to x squared plus 2 are going to be plus or minus I times the square root of 2. So they're not real numbers, which means this is not factorable over the reals. This is irreducible over the reals. Okay? So that means that the partial fraction decomposition is going to look like this. For x, we're just going to have an a over x. For x squared plus 2, we're going to have a bx plus c over x squared plus 2. Okay? And then that's that. So we want to solve for a, b, and c. So we're going to multiply through by the denominator to clear that fraction. We get 3x squared plus 5x minus 2 equals. Well, here the x's would cancel and leave me with a times x squared plus 2. Here, the x squared plus 2's would cancel and leave me with bx plus c times x. Okay? So, the cancellation method is only going to get me so far here, but I think I can get some useful information. Like if I let x equal 0, then on the left-hand side here, I'm just going to get negative 2. And on the right-hand side, I'm going to get 0 squared plus 2 is 2. 2 times a is 2a. b times 0 is 0 plus c, well, times 0. This whole term is going to be 0, right? So I just get negative 2 equals 2a. And that implies that a is negative 1. So that's useful information. But to get b or c, I'm not sure how I'm going to do that. I could plug in negative square root of 2 to cancel off the x, or to cancel off the a term, but then that's just going to be so messy to work with everywhere else. I'm not really sure that I want to do that. So maybe instead what I'll do is something like this. So I'm going to take this a step further. I'm going to distribute the a. I get ax squared plus 2a. And distribute the x. So I get plus bx squared plus cx. And then I'm going to regroup the terms in descending order in x, right? So I've got an ax squared plus a bx squared. Combining those like terms, I would just have a plus b times x squared. And then I have a cx, right? And then I have a 2a as my constant term. Okay? So what I can do now is called equating coefficients. So I can say the coefficient on my x squared term on the right-hand side of the equation should equal the coefficient on my x squared term on the left-hand side, so that a plus b should equal 3. Right? So I know that a plus b equals 3. And that's useful information because I know that a is -1. So really this is saying -1 plus b equals 3. Or in other words, b equals 4. Okay, so I've got a equals -1, b equals 4. And then the other coefficient that I can equate is the c, right? I know that c has to equal 5, right? C has to equal 5 just by equating coefficients. And by the way, I also know that 2a has to equal -2, which is exactly what I wrote down here, right? So I would get a equals -1 doing it that way as well. There you go. So equating coefficients is not a terrible way to go in this case. And I'm done now. So I can say the partial fraction decomposition for 3x squared plus 5x minus 2 over x times x squared plus 2 is a over x plus bx plus c, okay, bx plus c over x squared plus 2. Okay, and that's that. Again, you're welcome to check this by actually working it out. You should end up back here. Okay. So one more case to consider. The last case is when you have a quadratic factor that repeats. Okay, a quadratic factor that's irreducible over the reals and it repeats. And let's say it repeats m times. Now, if it repeats m times, then the portion of the partial fraction decomposition corresponding to q would be, well, you'd have one copy, and then another copy where you square it, and so forth, right? You'd have m copies, and you'd be increasing the exponent each time until you reach n. Okay? Let me give you an example of this. Okay, so let's say that we're trying to find the partial fraction decomposition of this nasty mess. X squared plus 4 is irreducible over the reals, right? If it factored, it would factor as x plus or minus 2i. So it's irreducible over the real numbers, and it's repeated twice. So that means since it's an irreducible quadratic, it's going to have, in the numerator, it's going to have an ax plus b. Okay, but that's just for one of the copies. Since it repeats twice, we need to have a second copy. And for that second copy, we need to have another linear factor, so I'm calling it cx plus d. All right? So that takes care of this first factor. The next factor here, x squared plus 3x plus 3. This is irreducible. If it factored, it would have to factor as 3 and 1, but 3 plus 1 is 4, not 3. Right? So this thing is irreducible over the reals. And since it's irreducible over the reals, it also has to have a linear factor in the numerator, so I'm calling it ex plus f over x squared plus 3x plus 3. But since it doesn't repeat, right, we only have one copy of that. We only have one partial fraction corresponding to that factor. Okay. And then we have x minus 2 squared. Well, this is just a linear factor, but it repeats twice. So linear factors just get a real number in the numerator, not a linear factor. They just get a real number. I have g over x minus 2, and then h over x minus 2 squared, right? I've got to have two copies where the exponent increases. That's the format. That's the format of the partial fraction decomposition for this thing, okay? So let me give you a completely separate example. I'm giving us a hint to use the cancellation method to get A. Well, of course, right? I've been using the cancellation method all this whole time. But let's do this. Fortunately, this has been factored for us already, so at least that much work has been done, because I have a feeling that solving for all of our A, B, C, D, E, F, G's is going to take quite a bit of work. So let's set up the partial fraction decomposition. We've got 2x to the fourth minus x cubed plus 13x squared minus 2x plus 13 over x minus 1 times x squared plus 4 squared. The partial fraction decomposition is going to look like a over x minus 1, right? Because there's just a linear term, it's not repeated. Plus, now here we have an irreducible quadratic, and we need two copies of it. So the first copy is going to look like bx plus c over x squared plus 4. And the second copy is going to look like dx plus e over x squared plus 4 squared. Okay, that's what the partial fraction decomposition looks like. Now to solve for a, b, c, d, and e, we need to multiply through by this fraction to clear the fraction. So we get 2x to the fourth minus x cubed plus 13x squared minus 2x plus 13 equals a times the x minus 1's would cancel, leave the x squared plus 4 squared, plus bx plus c times the x squared plus 4's would cancel and leave an x squared plus 4 and also the x minus 1. So we're going to have x minus 1 times x squared plus 4. And then here the x squared plus 4 squareds would cancel and just leave the x minus 1. So we're going to have dx plus e times x minus 1. Okay, so I'm saying hint, use the cancellation method to get a. Yeah, because if we plug in 1 for x, then these last two terms will just be gone, and I should be able to get a pretty easily. So if I let x equal 1, then we have 2 minus 1 plus 13 minus 2 plus 13 equals a times 1 plus 4 is 5 squared. And everything else is gone, right? So this implies 13 and 13 is 26, minus 2 is 24, minus 1 is 23, plus 2 is 25. So I get 25 equals 25a. Oh, look at how nice that works out. A is 1. Okay, so I know that a is 1. How in the world do I get the rest of these things? I think I'm going to have to equate coefficients. Yeah, I'm going to have to equate coefficients. So, goodness gracious, let's do this. So you know what? I'm going to do an additional step here. I'm going to say 2x to the fourth minus x cubed plus 13x squared minus 2x plus 13 equals a times x to the fourth plus 4x squared plus 4x squared would be 8x squared plus 16 plus, oh, do I really want to do this? This is nasty. Oh my goodness. So it's going to be bx plus c times x cubed minus x squared plus 4x minus 4 plus dx squared minus dx plus ex minus e. Okay. I'm gonna try to equate coefficients here. Oh no, I've got to do one more step. Let's do ax to the fourth plus 8ax squared plus 16a plus bx to the fourth. Bx to the fourth minus bx cubed plus 4bx squared minus 4bx plus cx cubed minus cx squared plus 4cx minus 4c and then the plus dx squared minus dx plus ex minus e. Okay, now let me get our coefficients together. So I know that I've got a plus b times x to the fourth. Now where that takes care of my x to the fourth. Now where are my x cubes? I've got an x cubed there and an x cubed there, and I think that's it. So I'm going to say negative b plus c times x cubed. Okay, and that takes care of my x cubes. Now where are my x squared? So I've got an 8a x squared, a 4b x squared, a negative c x squared, and then a d x squared. Okay, that takes care of the x squareds. Now where are my x's? I've got a negative 4b x, a 4c x, and a negative dx and a positive ex x. And then where are my linear terms? My linear terms are 16a negative 4c and negative e. Holy schmoly. Okay. Well, now I can equate coefficients, right? I can say a plus b equals 2. But I already know that a is 1, right? So really this means that 1 plus b equals 2, which means that b is 1. Okay, so a is 1, b is 1. Okay, I know that negative b plus c should equal negative 1. But I already know that b is equal to negative 1, so I have, or is equal to 1, so I get negative 1 plus c equals negative 1. That means that c is 0. I know that 8a plus 4b minus c plus d has to equal 13. Plus d equals 13. Well, a is 1, b is 1, c is 0, (12) plus d equals 13, so d is 1. How boring. Everything is either 1 or 0. D, and then I need e. I can get e from right here. Right? So I know that negative 4b plus 4c minus d plus e has to equal negative 2, right? Equating the coefficients. B is 1, c is 0, d is 1. So negative 5 plus e equals negative 2. Add the 5 and you get e equals 3. Okay, so finally something that wasn't that wasn't 0 or 1. Now if I plug this into this last equation, it should work out that this equals 13. So this is a way that I can maybe check my work to see if I went wrong somewhere. But a is 1, so I get 16. C is 0, so I get 16 minus 3. 16 minus 3 is 13, sure enough. Good. So that gives me confidence that this partial fraction decomposition is correct. So what I can say now is that the original expression, 2x to the fourth minus x cubed plus 13x squared minus 2x plus 13 over x minus 1 times x squared plus 4 squared is equal to a over x minus 1 plus bx plus c, right? B was 1 and c was 0, so this is 1x plus 0, right? Or in other words, just x. So bx plus c over x squared plus 4 plus dx plus e over x squared plus 4 squared. And there's my partial fraction decomposition. Again, you're welcome to do this addition to make sure that you end up back here, but you should if you do all the addition correctly. So that's that. That's how partial fraction decomposition works. Thank you for tuning in.